The rotating C ring is composed of 8 to 12 copies of the C subunit. The protons pass through a channel that is formed at the interface of the C ring and the A subunit of the F0 complex. When the C ring rotates, the gamma and epsilon subunits rotate along with it. However, as I mentioned before, the alpha-beta hexamer of F1 does not rotate because it is anchored by the delta subunit. The delta subunit is in turn bound to the B subunit, which is embedded in the inner mitochondrial membrane. Let's situate ourselves within the mitochondrial matrix so that we can look down on the hexamer. In this view, the gamma subunit is in the middle, surrounded by the 3 alpha-beta heterodimers. We will in particular focus on the beta subunits, where the actual catalysis takes place. In Boyer's explanation of ATP synthesis, which is also known as his binding change mechanism, each beta subunit can exist in one of 3 different conformations at a given time. One of the conformations is called open. In the open conformation, the substrates of the ATP synthesis reaction, namely ADP and inorganic phosphate, can bind to the open beta subunit. Another conformation is called loose. Although it seems a little bit counterintuitive, in the loose conformation, both of the substrates are associated with the beta subunit. They could be considered to be loosely locked into the active site, in comparison to what is the next conformation. This third and final conformation is called tight, and this is where the substrates are pushed together in an optimal geometry to catalyze the synthesis of ATP. All 3 different possible conformations of the beta subunit, open, loose, and tight, exist at the same time among the 3 different beta subunits in the F1 hexamer. Boyer's proposal of a binding change mechanism suggests that as the gamma subunit rotates, each beta subunit sequentially moves through the open to loose to tight conformations. Let's start with beta 1 in the open configuration, beta 2 in the loose configuration, and beta 3 in the tight configuration. As the gamma start rotates 120 degrees, beta 1 switches from open to loose, locking in the substrates. Beta 2 in turn goes from loose to tight, driving the catalysis of ATP. And beta 3, that was originally tight, switches to open, releasing the ATP product. As the gamma subunit continues to rotate, the sequence continues. Beta 1 now goes from loose to tight, driving the catalysis of ATP. Beta 2 goes from tight to open, releasing the ATP product. And then beta 3 goes to loose, locking in the substrates that came in after the original ATP product left. Rotation of the gamma subunit causes the protein conformations to change within the beta subunits, varying each subunit's binding affinity for the substrates. The catalytic effect of the beta subunits will also be different, ultimately leading to the release of the product. Once ATP is released, new substrates can then come in and bind. And as the rotation continues, the cycle of ATP synthesis repeats. It is worth noting that the beta subunits cannot all assume the same states at the same time. 3 beta subunits are therefore staggered in conformation relative to each other. So there's a domino effect of structural changes that propagates around the 3 beta subunits of the hexamer. The F1-F0 complex converts the mechanical energy from the proton flow into the rotation of the gamma stalk, which is then transformed into the conformational changes in the beta subunits of the hexamer, that in turn is converted to the chemical energy in the bonds of newly synthesized ATP. Let's now take a look at this in detail in the animation.